All right, here's our exponential modeling problems. We're going to do two problems from the notes, and then the rest will be for you to do on your own as practice. So numbers 1, 2, and 3 are all what we call growth problems. So the situations are where something is growing rapidly at an exponential rate. So I'm going to do number 1 as a model for you, and then leave you to do 2 and 3 on your own. And then 4 and 5 are what we call exponential decay problems. So it's something that's getting smaller rapidly. And I'm actually going to do number 5 as a model for you, and then you can do number 4 on your own. Okay, so number 1, if you haven't already read the problem, please pause your video and do that now. So we have this situation where a bunch of bacteria organisms are found, and initially at time 0, when no time has passed, 200 bacteria are found. After 3 hours has passed, it is now at 32,500. And so part A gives us this exponential equation. Let's talk for a minute about what the variables stand for. So remember that E is not a variable. It is the number that represents 2.71828, and so forth and so on. Y is a variable that stands for the total amount of organisms at a particular time. It depends on how much time has passed, T. C is the initial amount at the very beginning of the situation when no time has passed. So when we find the 200, that's at time 0. E is not a variable. K, right here, is the rate of growth or decay, depending which kind of problem you have. And then E is approximately 2.71828, never ends, never repeats. So we're going to plug in the things that we know, which we know that C is 200. So that's the beginning amount. So this makes C a constant. It will always be 200. Whereas Y, the total amount, and T, the time that has passed, will change. So those will stay variables. C will be a constant because the initial amount, 200, will always be the initial amount. And K is a constant, but we don't actually know that yet. The problem didn't tell us that, so we are going to find it. So here's my starting information. At time 0, so no time has passed, C was 200. Then after the nap, 3 hours have passed, so T is 3. Our total organisms were 32,500. This is going to be a Y value for us. At a specific time T, this was the Y. So when we plug all this information in, you can see we have this equation where we can solve for K. And this is very similar to when we solve for the A value in functions, and then we go back and plug that A, which is a constant. We plug it into the general form of the equation. Okay, that's all I had to say about that. I said like I had more information. That's basically it. So because this equation is an exponential form, and the variable I'm trying to solve for is in the exponent position, I know that eventually I will need to rewrite this as a logarithmic equation because logs and exponentials are inverses of each other, so that's how you would solve an equation for a variable, by doing the inverse operation. But I can't rewrite it as log now because of this constant 200 that's in front. I need the exponential piece isolated before I apply a log. So I'm going to start by dividing by 200. on both sides. This gives me 162.5 equals e to the 3k. So now I am going to rewrite as a log base e of 162.5 equals the exponent 3k. Solving for k, I divide both sides by 3. So in my classroom, we were using the yellow TI Inspires to calculate this value. If you're at home or you don't have a TI Inspire but you have access to Desmos graphing calculator, it will do custom log and bases there. All right, so also don't forget log base E is the same as natural log, so you could just find natural log of 162.5 over 3. Either way, whatever you decide to do, whichever route you take, you're getting k to be approximately 1.697. So then now this is a constant. We know our constant c and y and t go back to being variables. So now we have this equation that represents the situation, and we can use it to answer B and C. So B says if you were to leave the bacteria alone, how many would there be 24 hours after you found them? So we can take this equation we have now, put 24 in for the T, and put that in your TI Inspire or Desmos or another calculator that can handle base E. And this gives you approximately 9.75 times 10 to the 19. And that is a lot. That's all I have to say about that. And this number actually does a really good job of showing exponential growth. We talked about how exponential growth, the growth starts out small and then starts increasing very rapidly, very quickly. And that's what's happening here. After we started with 200 and then 24 hours later we have this many. Okay, then part C, you decide to disinfect your closet when there are 6,152,000 bacteria. How long will you have to wait? So now what we know is the Y. This is the total amount of bacteria, and we're trying to solve for T. So I'm going to plug that in for the Y. 200 is my constant, e to the 1.697 t. So now we have a situation similar to when we solved for k in part A. I need to divide off the constant. So that gives me 30,760 equals e to the 1.697 t. This is an exponential form. It is isolated. To get t out of the exponent spot, I do the inverse operation of both sides, which is logarithm. So rewrite this as log base e of 30,760 equals 1.697 t. So log base e is the same as natural log, so I'm going to write that down, of 30,760 equals this. Divide both sides by 1.697. Go to whichever calculator you are using to compute this fraction right here, and you get approximately 6.09 hours. Okay, so 2 and 3 are also growth problems that work similar to this one, so I'm going to leave those for you to do on your own. 4 and 5 are decay, so let's look at number 5. If you haven't read the problem, please pause your video and go read that now. Okay, in this situation, instead of something growing really quickly, it is reducing, dying, decaying very quickly. So the initial situation is that there are 15 kilograms of a radioactive substance. And we know that it has a half-life of 30 years. So every 30 years, half of it is gone. So in part A, find the exponential equation, which describes the amount of radioactive material. Now notice this is the same equation as before, and the K value is what is going to create the growth or decay situation that we need. So we have to start like the other problem and figure out what K is first. So remember that C is the initial amount. So C is 15 when time was 0. And we know that it has a half-life of 30 years. So when T is 30, the Y value there is half of whatever 15 is. That's what a half-life is. So we take half, which is 7.5. So now we're going to plug these things in. We've got 7.5 is the Y value equals 15 times E to the K times T, which is 30. And notice 30 years hasn't passed. We just know that 30 years is the half-life. So we're going to use it to figure out the rate of decay. So I need to divide both sides by 15 to isolate the exponential piece. So this gives me 0.1. Sorry, it's a half, 0.5 equals e to the 30k. I rewrite this as log. So log base e of 0.5 is equal to 30k. In other words, log base e, or natural log, of 0.5 equals 30k. Divide both sides by 30. And k is approximately negative 0.023. So plugging this back into my equation, I'm going to be changing y and t back to general variables here. C and k are constants. So C is 15 times e to the negative 0.023 t. And then part B, how much radioactive material will be left in 40 years. So 40 is my time. I'm going to put 40 in for t. And then we go to a calculator to do all that work for us. And we get approximately 5.95 kilograms. And then on this last one, John wants to know, how long will it take for the substance to decay to 10% of its original mass? When will this happen? So that number is going to be a Y value. Y stands for the total amount at any particular time. So I kind of would want that actual number. So I'm going to take a second and just calculate what 10% of the original mass is. So 10% as a decimal, remember you move the decimal 2 places to the left, so it's 0.1 times the original amount is 15. That gives me 1.5. So that's a Y value when time is, we don't know, because that's what we're trying to figure out how long that takes. So I'm going to put 1.5 equals 15e to the negative 0.023t. Solve for t, I'm going to rewrite this using log. First, I'm going to divide off this 15 here. So that gives me 0.1 equals e to the negative 0.023t. Now I can rewrite as log base e of 0.1 equals that. So log base e is the same as natural log of 0.1. Divide both sides by negative 0.023, and t is approximately 100 years.